Namaskaram. In last class, we have seen that higher order partial derivatives and the relation between partial derivative and continuity. In this session, we will see the concept of total differential in multivariable calculus. Okay, let's start. We know that the derivative of a function at a particular point x0. It is given by this formula, limit delta x tending to 0, f of x0 plus delta x minus f of x0 by delta x. Then if this limit exists, then we can say that derivative exists at x0 and denoted by f dash of x0. Okay. And this f dash of x0 has three important properties. The first one is the graph y is equal to f of x has a unique non-vertical tangent at the point x0 f of x0. That means, that is, suppose this red curve is or y equal to f of x, then we consider a point x0, and suppose it is differentiable and f dash of x0 exists, then this f dash of x0 means it is the slope of this tangent. That means it has a unique tangent at this point. Okay, and the slope of this tangent is given by this value or this formula f dash of x0. Okay, that is the first one. The second property of the derivative is if f is differentiable at a point, then it is continuous at that point. Okay, that means there is no break at that point if it is differentiable. The third important property is f can be closely approximated by a linear function near x0. Anyway, this closely means it's a relative term. Let us see how much close it is. A linear function means a function of the form y is equal to mx plus c. Okay. Okay. Consider a graph like this. Here this blue curve is our function f of x, and f of x0 is known, and our aim is to approximate the value of this function using a curve or a straight line y is equal to mx plus c. Okay, so we are going to approximate the value of the function at this point x0 plus delta x using the value of the tangent at this point. Okay, so first we have to find equation of this tangent, then next we approximate the f of x0 plus delta x0 using the value on the tangent. That is idea. Then we have to measure the error. Okay, then how to find the equation of the tangent? We know that the slope of this tangent, that is nothing, f dash of x0, and also we know that this tangent is passing through x0 f of x0. Okay, using these two idea you can easily find the equation of the tangent. So what is the equation of this tangent? Then how to find the equation of the tangent? We know that every straight line is of the form y is equal to mx plus c, where m is the slope. Slope is not, that is f dash of x0. So we can assume y is equal to f dash of x0 into x plus c. Then also we know that this straight line or this tangent passing through x0 f of x0. So you can substitute this point. So what happened? Okay, so left hand side become f of x0, that is our y value. So right hand side is f dash of x0 into x0 plus c. So what do you see? C is like this, f of x0 minus f dash of x0 into x0. So you can substitute this c in this formula that gives equation of the tangent at this point with slope f dash of x0. That is y is equal to f dash of x0 into x plus f of x0 minus f dash of x0 into x0. Okay. Okay. So now we are ready to approximate the value of the function using the value of this tangent. Okay, because now we have the equation of the tangent. Suppose that this function value is unknown. Suppose we have only f dash of x0 and f of x0. We have only f dash of x0 and f of x0. And the value of the function at x0 plus delta x is unknown. Then you can approximate the value using the corresponding tangent value because this tangent is known. So what is approximation? So approximation means we have to find f of x0 plus delta x. We don't know what is the value of the function. We assume that our function value is unknown. Then you can approximate this using the value of the tangent at this point. That is nothing, y of x0 plus delta x. And what is y of x0 plus delta x? You simply substitute x by x0 plus delta x. That is nothing, that is f dash of x0 into delta x plus f of x0. Why? So that is because you consider y of x naught plus delta x. What is that? That is equal to f dash of x naught into you have to just replace x by x naught plus delta x. That is x naught plus delta x plus there is no term containing x, so no change in this term. That is same. So our one time is f dash of x naught into x naught. Other time is minus f dash of x naught into x naught. So you can cancel these two terms. The remaining term is f dash of x naught into delta x. That is the first term plus f of x naught. That is our second term. So this is the approximate value of the function at x naught plus delta x using the tangent at x naught. Clear? So naturally there is an error. This is our difference. Okay. Okay. Now we assume that this f of x naught plus delta x is equal to f of x naught plus some change in f. Okay, actually we don't know what is delta f. Okay, but now we approximate the same f of x naught plus delta x using this quantity. That means f of x naught plus f dash of x naught into delta x. Okay, so the common term is f of x naught. So our the change delta f, that means the change in f, that is our delta f. So we approximate our delta f using f dash of x naught into delta x. And what is delta f? Delta f is the corresponding change in f. That means f of x naught plus delta x minus f of x naught. Clear? So delta f is nothing, it is the change in function, actual change in function. And now we approximate this delta f using f dash of x naught into delta x. Clear? So what about the error? So we approximate our delta f. This is delta f by this quantity. So error is nothing, this one. Clear? That's why we define our error as delta f minus f dash of x naught into delta x. So this is the error in this linear approximation. This is linear. Okay. So this is the error in this linear approximation. Okay. Next we have to check how much this approximation is better. My claim is this error is less than distance between these 2 points. That means this error is less than delta x. So whenever delta x is small, that means this approximation is very close to x naught, then our error, this error is less than the distance between these 2 points. So points are close together, then error is very, very small. Okay, then how to establish this one? For that we consider this limit delta x tending to 0, error by delta x. And this is equal to limit delta x tending to 0. What is our error? Error is delta f minus f dash of x naught into delta x by delta x. And what about this limit? And this become, first we split this limit as two limits, limit delta x tending to 0, delta f by delta x minus limit delta x tending to 0, f dash of x naught into delta x by delta x. Here delta x is only tending to 0, so you can cancel these two delta x, so this become f dash of x naught. Okay, then again, what is our delta f? Delta f is nothing, it is the actual change in function, that is f of x naught plus delta x minus f of x naught by delta x minus, and here this term does not depend delta x, so the limiting value is same as f dash of x naught. Okay, and what about this limit? This is nothing, this is our f dash of x naught, so this become f dash of x naught minus f dash of x naught, so this value equal to 0. As a conclusion, the limit delta x tending to 0, error by delta x is 0. And what is the meaning? This means whenever delta x is small, this error is less than delta x. Then only this ratio is tending to 0. Right? Suppose delta x is 0.1. Then error should less than 0.1. Then only the ratio is tending to 0. You got it? So that is the idea. So since this limit is 0, this means error is much smaller than delta x whenever delta x is close to 0. Delta x is close to 0 means our point is close to x naught. So if we approximate linearly using nearby points of x naught, then the approximation is better because that error is less than the distance between the point. This distance is very small. So error is also very small. Clear? So this is the idea. When the 2 points are close together, these are the 2 points. The magnitude of the error in the approximation will be much smaller than the distance between the points. Okay. This is the meaning of closeness in linear approximation in one variable calculus using our f dash of x naught. The similar results extended in two variable calculus. Okay, so in the case of two variable calculus, we have to define delta f and this approximation. Here we approximate our delta f by, this is our delta f, we approximate our delta f by f dash of x naught into delta x, right? Okay, here we approximate this delta f by f dash of x naught into delta x, right? And delta f is difference between function at x naught and our new point x naught per delta x. Similarly, we can define delta f in two variable calculus and we extend this approximation using partial derivatives. That's all. Okay. Okay, consider our two variable calculus, two variable function, and this is our point x naught y naught. Suppose we know the value of the function at this point. Our aim is to approximate the value of the function at this point. Okay, a change in x and change in y. Right. So actually we don't know what is the value of the function at this point. So we are going to approximate using the similar rule. And what is our delta f? Delta f is the difference, actual difference. Suppose our function at this point is here, this height. So this height is nothing, this value f of x naught plus delta x, comma y naught plus delta y. And the difference between this value and this value, that is our delta f. Our aim is to approximate the delta f. Okay, what is a similar result for delta f in two variable calculus using partial derivative? Partial derivative at the point x naught y naught. Okay, in two variable calculus we have two partial derivatives at this point. So we approximate delta f like this: f dash of uh, uh, fx at x naught y naught. That means partial derivative of f at x naught y naught into delta x plus fi of x naught y naught into delta y. Okay, so we evaluate the partial derivatives at x naught y naught with respect to x and y, and this into delta x plus this into delta y. This is the analogous extension or analogous definition of delta f, approximation of delta f like one variable calculus. Okay. So what is the error in this approximation? As similar to one variable calculus. In one variable calculus, the error is delta f minus this approximation. Okay, of course, here also our error is defined like this: error equal to delta f minus this quantity. What is our approximation? Okay, so this approximation is better only when this error should less than distance between these points, whenever this point is close to this one. Okay, so that is our important property of this approximation. Okay, if this is true, then our approximation is good. In general, this is not true, but most of the application, or in all applications, most of the applications, this is true. That means this approximation is better. This error is less than distance between the points. Okay. In general, this is not true. There are theoretical functions doesn't satisfy this equation, this criteria. But in most of the applications, this error is less than distance between the points whenever the point is close to x naught y naught. Okay, next we will verify this concept with a simple example. Okay, that means we evaluate this actual delta f and we evaluate this approximation and evaluate the error, and we have to check whether this error is less than distance between the points or not. Okay, before that we have to define a new concept that is called a total differential. Okay, this is the definition of total differential of a function f at a point x naught y naught. dz is equal to fx at x naught y naught into dx plus fy x naught y naught into dy. And what about this one? This is nothing. The intuition of this definition is nothing. It is from this expression, because we know what is delta f. Delta f is the actual change in our function from x naught y naught to x naught plus delta x and y naught plus delta y. And this is our linear approximation. Okay, actually we define this linear approximation as dz. So dz is nothing, it is the approximation of delta f, the change in function. Clear? So and this function is called total differential of this function f at x naught y naught. So dz is nothing, dz is the approximation of delta f actual change in function. Okay. So similarly, we can extend this concept to in a general formula by removing x naught and y naught. So in general, we can define total differential as a function like this: fx into dx plus fy into dy. Clear? Okay. Anyway, for better clarity, we will consider an example. What is the actual difference between delta f and dz? Okay, delta f is the actual difference. This is the approximation. Okay, let us see. So you consider this problem. Use a total differential to approximate the change in the function z is equal to fxy. What is fxy? Xy square. From its value at 0.51 to its value at 0.503 and 1.004. There is a slight change in this point, right? Compare your estimate with the actual change in z. That means we have to find original change and change using this total differential, approximation using this total differential, and we have to compare what is the difference between original change and or approximation change. How much difference is there? Okay, let us see. Okay, first we are going to find the actual change in this function. Okay, that is our delta z, or delta f. Okay, whatever be no problem. So first we are going to find the actual change delta f. How to find? You simply evaluate value of the function at this point, and also you can evaluate the value of the function at this point. Then you take the difference. That's all. Okay, so what is that? So this is the value of the function at this point, and this is the value of the function at this point. So you take the difference. So difference is like this. So this is the actual change in our function, right? So next we are going to approximate this delta z or delta f using our dz or our total differential. Okay. Okay, we have to approximate this using dz. What is dz? Dz is fx, x naught, y naught. What is our point? Our point is 0.5 and 1. So fx, derivative of f with respect to x at this point into dx plus derivative of f with respect to y at the same point into dy. And what is dx and dy? Dx is nothing. Dx is the change in x and dy is change in y. What is change in x and change in y in this problem? Yes, dx is 0.503 minus 0.5, that is 0.003, and similarly dy is 0.004. Okay, so to find this dz, we have to find fx and fy. The function is here. This is our function. F is equal to xy square. So you simply differentiate with respect to x and y and substitute these 2 points. So what is fx 0.51 and what is fy 0.51? Okay, so fx is y square and fy is 2xy. Then what about fx 0.51? So here y value is 1. So this is nothing 1 square. And similarly, what is fy 0.51? That is 2 into 0.5 into 1. Okay, now everything is clear. We can substitute everything in this formula for evaluating dz. So this dz become, okay, this is equal to like this. This is our fx at this point into dx. Change in, oh, this is actually, sorry, this is 0.003 plus 2 into 0.5 into 1. That is our fy into change in y. Oh, sorry, point is here, 0.004. Upon simplification, what happened? This is equal to, yes, this is equal to 0.007. So this is the approximate change in our function. Okay, this is our actual change. Actual change is 0.007032048, and this is the approximate change using our linear approximation. Then how better? How much better this approximation? Okay, that's our next concern. Okay, so dz equal to this one. I'll take the derivative and substitute all the values. Then this become 0.007. Okay, then the error is nothing. Error or absolute value of the error. You simply take the modulus. So that is delta z minus dz. The difference is 0.000320048. Okay. Next we have to compare this error with the distance between these 2 points. Okay, our claim is this error should less than distance between these 2 points. Okay, that's our idea. Then what is the distance between these 2 points? So distance between 2 points in plane, that is very clear. That is, suppose this is x1, this is x1 y1, and this is x2 y2. Then x2 minus x1 whole square plus y2 minus y1 whole square. So this d become square root of the difference between x, that is 0.003 square plus 0.004 square, and that is equal to 0.005. Okay, so this is the distance between these 2 points. So next we have to compare how much less this error than this distance. Okay, okay, it is clear that our error is less than distance between the point. Then how much? For that we consider the ratio, error by the distance. So our error is this one and this is our distance. If you take the ratio is less than 1 by 150. Okay, you can verify it. This is less than 1 by 150. Then that is meaning. What is the meaning of this expression? This means our error is 150 times less than distance between the points. Clear? It means our error is 150 times less than distance between the point. That means our approximation is very better, very good. Okay, our approximation is good. Okay, then there is a natural question: what is the use of these type of approximation? Here we approximate our function nearby a point using a linear approximation. What is the use? The main use is machine can easily handle linear functions than nonlinear function. This is a nonlinear function. Okay, so machine can easily handle linear functions. And another application of this type of approximation is in some practical situations. Maybe we know the function at a particular point, but we have to find function nearby point without knowing original function. Suppose original function is unknown, but we know a specific value of the function, that means function at a particular point. Suppose you have to find or you have to approximate function nearby points, so you can use this technique. We know that if function is unknown, no problem. If derivatives are known, you can approximate nearby points using this linear approximation, and this approximation is better because error is always less than distance between the points. Okay, these are the two applications of this type of linear approximations. Okay, so that's it. So in next session we will see the more general concept of this approximation, that is called local linear approximation. Okay, thank you.